Alright, slide 19 is very similar to one that we did before, which was slide 15 if I recall. Um, there is one slight change to this one, and it's because we have a throwback question. This one involves circular here. So it tells us the condition that the passengers feel weightless for a moment when they are over here at point C. So that means before we can do anything, we need to figure out, well, how fast is this roller coaster car going at point C? You see there's a minimum velocity that it needs to have so that it can complete the circle. So if we go back to circular motion, then we remember that the centripetal acceleration is equal to velocity squared divided by the radius. And we do know what the radius is. We're looking for the velocity. And so the condition that you feel weightless at point C, that's telling us that the acceleration is going to be equal to gravity. In other words, gravity is providing the centripetal acceleration. So I know what gravity is, I know what the radius is. Now we can solve for that minimum velocity. And when we move this around, you should see it looks familiar. It's just the square root of r times g. Now we talked about all those different situations for circular motion and the minimum velocity. So the one for the roller coaster, making the loop-to-loop, square root of rg. Okay, so let's plug numbers in, get an answer. Velocity is equal to the square root. My radius is 12, and my value for gravity is 9.8. So that means my velocity has to be equal to 10.84. So that is our velocity at point C. Okay, so let's change to a different color. And now we'll start talking about, well, what type of energy do I have at part C? So at part C, we have potential energy of the gravitational flavor at point C. And we also have that kinetic energy at point C. That energy came from, it originated from point A. So that's equal to the gravitational potential energy that we have at point A. So that is our setup. Now let's look at the individual variables. Let's expand out our equations. So at point C, we have mass times gravity times the height at point C plus 1/2 mass times velocity squared. And we just solved for that velocity, so that's good. That is equal to mass times gravity times the height at point A. And that is our overall goal. What is the height at point A? That's what we're trying to find. So looking at this, do they tell us the mass of the roller coaster car? And the answer is no. And the reason why is because we don't need it. You'll notice that mass is the same in all three parts, and so we can factor that out. It's gone. Okay, so that means to solve for the height at A, all I got to do is just divide g. Alright, so I'm going to divide everything by g. And when I divide everything by g, I've got to clean this up. So this is going to give me hc times g divided by g. So g over g is going to just cancel out. Actually, you know what? Let me do this the right way. Divide by g and divide by g. I'm putting the g on bottom with the 2. So it's 1 over 2g. and I'm dividing by g here. Alright, so that's gone. Well, that's gone, and we can see there's a g in that point. Alright, let's clean this up. It looks messy. Let's clean this up. So that goes away. That goes away. And that's how I solve for the height at A. So it's simply equal to the height at C, and the height at C is not the radius. The height at C is the diameter. So my height at C is twice the radius. So if my radius is 12, then my height at C would be equal to 24. So this is 24 plus, let's go ahead and put the v squared on top. So my velocity was 10.84 squared divided by, put the parentheses, otherwise the calculator's not going to do the math right. 2 times 9.8 goes on bottom. Okay, and if we put that all into the calculator, it will spit out an answer of, I get an answer of 29.995, which when I round the 5 up, it's going to round off to exactly 30.00. And that would be my height in meters. That's it.